Okay, so today is the 15th of April, and we're at precipitation reactions. So, if you've got two substances in aqueous solution, like we had in our calcium chloride and our sodium chloride and our silver nitrate, we can look at those two things, and you know how to predict products, right? We did this back in Chapter 8. So let's take, for example, our silver nitrate, NaGNO3, and let's add that to sodium chloride, NaCl. Okay, pretty easy. If these things react in a double replacement reaction, can you predict what the products would be?
Yes.
Okay, so give me one product. Somebody with blue or green on. Okay, one of you two. Okay, silver chloride. And somebody with red or brown on, give me the other product.
Sodium nitrate.
Sodium nitrate, okay. Okay, silver chloride and sodium nitrate. Good, and that's a correct prediction of products. Now, what we need to do, what causes something to precipitate? So if we've got something here, it's soluble, it's in solution, what does a precipitate indicate? Something has formed which is insoluble. Suddenly we've got something in that mix that is not soluble. So it comes out of solution, it precipitates. So I want you to get the table, the predicting solubility table you had yesterday. You can get it from your quiz, you can get it from your book. And I want you to look up the solubilities for both of these compounds. So we've established that sodium nitrate is soluble, looking at the guidelines for solubility. So we find that silver chloride is insoluble. What do you think that precipitate was then? It was silver chloride. We formed an insoluble product. This is really the heart of what we do in this chapter. You're looking at products, you're predicting products, you're determining solubility, and you're predicting if there will be a precipitate formed, or if everything's just going to stay in solution and hang out. So in those things, when I added two solutions together and no precipitate appeared, all the possible products were what? Soluble, exactly. It's not hard, but we've got a couple steps to go through. So we'll stick with our silver nitrate and sodium chloride example. And what we're going to do is actually get all the way to the point of writing a net ionic equation to show what happens and what doesn't happen when we put these two things together. So I will probably be so mean as to just give you the words silver nitrate, sodium chloride, and tell you go, and you'll start from there. But here I've gone ahead and I've written the equations for you. The first thing we want to do, we know that these are in aqueous solution, right? So how do we show the form that they've taken? Well, how do we show them going from a solid to being in an aqueous solution? Dissociation equation. So we're going to write a dissociation equation for each of these reactants. So we have silver nitrate in solid form, dissociating in water. Name me one ion, somebody in black or gray. One of the ions this will dissociate into. Silver what? Ag1+, and that's going to be aqueous. And what's the other ion? Be nitrate. NO3 1-, also aqueous. Okay, now let's look at sodium chloride. So we have sodium chloride dissociating in water. What are the two ions that it's going to dissociate into? Somebody I haven't heard from yet. Na 1+. Aqueous. And what's the other one? Cl 1-, also aqueous. Okay, we've written our two dissociation equations. This is our first step because we now know what's going into this whole kit and caboodle. That's actually our first step. That was step 1, just writing the dissociation equations for each of these things. Step 2 is a skill that we learned back in Chapter 8. We're going to predict products. So if we combine these two things, the potential products are sodium nitrate and silver chloride. Now, we know that this was in aqueous solution. This was in aqueous solution. We don't know what state these are in until we look up their solubilities. Now, we already did that as sort of a practice run. So sodium nitrate was soluble, yeah. So that one's still going to be aqueous. The silver chloride, however, was insoluble. So it's going to be a solid. That will be a solid. So that's our second step. We've now filled in all of our state stuff in the double replacement reaction. Now we're going to take the two things we've learned and we're going to smash them together. I know you love it when we do that. So in step 3, we're going to take these these dissociated ions, and we're going to put them all together in one big equation as a recognition of what's actually happening here. So we're going to take our Ag1 plus our NO3 1 minus plus our Na1 plus our Cl 1 minus, and every last one of these is aqueous. So we're going to list all of the ions that are participating on the reactant side. Now we're going to put all of the ions on the other side that are still in an aqueous form. So which ones are we going to put there? Sodium and nitrate. So we've got Na1 plus NO3 1 minus. What about the silver chloride? Is it in the form of dissociated ions? No. It's a solid. So that means it formed a compound. We're going to show it as such. So we're going to write AgCl. There are no charges on this. This is not ions playing around on their own, you know, loosey-goosey. And this is a solid, and we will show it that way, where these, of course, we're going to show as being aqueous. Okay? That's our third step. Do you want to practice a couple, just going through those steps? Okay. And then I'll show you, what comes next. Okay, so we've got copper 2 nitrate and potassium bromide. We want to, first of all, do a dissociation equation for each of them. This is good because we've got a slightly more complicated formula. All right, for our copper 2 nitrate, name me the first ion that you're going to see appear in solution. We're going to have Cu2+. And that will be aqueous. And what's the other ion that's going to come out of here? Somebody with strings on. Somebody with a hoodie. Okay? Nitrate. So NO3. Whoa, that's a terrible 3. 1 minus, also aqueous. Okay? And what about the potassium bromide? Somebody in green. Give me one of the ions. Potassium in aqueous solution. Somebody in, I don't know, something else. Man, black or gray? Go ahead, David. Which is Br1 minus, also aqueous. Okay, so we've got our dissociation equation done. That's our first step. We can see the ions that this splits up into. Anna. Okay, and I forgot my coefficient there, because that's going to break up into 2 moles of nitrate ions. Do you all understand why?
Yes.
Okay, good. So now we're going to write a double replacement reaction. We're going to put both of our products over here, or both our reactants, rather, over here. And what form are these things in?
Aqueous.
Aqueous. If we mix them together as solids, nothing's going to happen. We only have a chance of getting a reaction if they're in aqueous solution. Okay, and if a double replacement reaction did occur, what would our products be? Copper bromide, CuBr2, and potassium nitrate, KNO3. 3. Is this balanced? No. How could we balance it? Okay, now we're balanced. Now we have to look up what? We have to look up solubilities and predict solubilities for copper 2 bromide and potassium nitrate. Okay. So anytime that both of your potential products are soluble, no reaction happens. They all just keep floating around in solution, and they don't form a solid. That's what happened when I mixed things and there was no precipitate. We had 2 potential products, both of which were soluble. Okay? So now, does that feel fairly easy, fairly comfortable? Okay. Now let's go that 4th step. Approach that idea of, remember I talked about net and gross the other day?
Yes.
So now we're going to do the net and gross thing. We're going to do net ionic equations. Before we can get to the net equation where we take stuff away, we have to do the overall equation, which is kind of like the gross equation. So let's practice with an example that's going to form a precipitate. So we're going to go back to the silver nitrate and sodium chloride, and this is the equation that we wrote way back a number of slides ago. This is showing us all of the ions that are participating, and this is kind of like the gross ionic equation. Okay? Yeah, gross as in your gross paycheck. Now, gross is not a real term that's applied to it. I'm using that as a metaphor. We're going to then remove stuff and come up with the net ionic equation. Okay? So it's actually called the overall ionic equation. Terrible handwriting. The overall ionic equation, but we can think about it as like the gross, like your gross pay before you get all your deductions taken out. So what we're going to do next, you've been spectators. So if you're spectating at a track meet, are you running around the track? No. Are you throwing the shot? Are you jumping over something? No. You're standing around with your hands in your pockets, maybe you're eating nachos. That's about it. Spectators are those who are not participating in the action. So, if we look at this equation, we have some ions that are not participating. We call them spectator ions. They're in the exact same form when we get to the reactant side as they were in the product side. Name me one of these spectators. Sodium. Sodium's doing nothing. It's in an aqueous solution over here. It's still in an aqueous solution over here.
Nitrate.
Nitrate is the other one. Nitrate is in an aqueous solution over here, aqueous solution over here. It's doing nothing. Those are our spectator ions. We cross those out and we recopy only the ions now that are participating in a reaction. So we get silver, aqueous, 1 plus chloride, 1 minus, aqueous, forming AgCl, solid. That is a net ionic equation. Okay, this is your net ionic equation. This is the final step. So this shows you that silver and chloride ions are participating in this equation. Everybody else didn't do a thing. They get crossed out. So it's a 4-step process. Let's review the 4 steps in order. Dissociation equation. Step 2. Step 2. Make your double replacement reaction. Predict the products that could potentially occur. And there's another piece to step 2. What is it? Check solubility. So you have to check the solubility of your product. 3rd step is what? So we cross out the spectator ions, and that leaves us ready to do step 4. Okay, so 4 easy steps. Write your dissociation, write a double replacement and predict products, check the solubility of those products, write your gross ionic equation, cross out any spectator ions, and then recopy using only the ions that are participating, which gives you your net ionic equation. Not so hard, right? Okay. You'll have number 16 is the homework. It is assigned. It is due tomorrow. It's a 3-part problem, so you get to do 3 of these for practice. Then I will give you a take-home FIP quiz. The key will be available tomorrow for you to check it yourself. Questions, comments, concerns?
Are we gonna have